Hello, welcome to lecture 15 of the course. In the last lecture, we derived the quantum master equation in its Lindblad form. In this lecture, we'll see how this Lindblad master equation can be applied by exploring some examples. In the last class, we have derived the quantum master equation and it is of this form. Here, rho of t represents the density operator which describes the quantum state of the system, and in this equation this italicized capital L is the Lindblad superoperator. Gamma alpha are the dissipation or diffusion coefficients, and it is actually equal to twice of the real part of the function z alpha plus, and z alpha plus is defined like this. And in the quantum master equation, Hs represents the Hamiltonian of the system, and H effective is the effective Hamiltonian which results from the system reservoir interaction. It only shifts the system energy level, hence mostly this term H effective can be neglected. We will now discuss some examples. However, before that, let me make some comments. We will write the Lindblad master equation in the following form. Rho dot is equal to minus I by h bar, commutation between the system Hamiltonian and the density matrix. This time I am not going to consider the effective Hamiltonian because its contribution or it hardly changes any physics, so we'll ignore that. Then the next term would be sum over alpha, gamma alpha, this Lindblad superoperator as alpha, rho. So this is my Lindblad master equation. Here this operator S alpha, which is the system operator, it actually tells us how the system relaxes or transit from one state to another because of interaction with the reservoir. And this is the reason also sometimes this S alpha, it's also known as the relaxation operator, because it simply tells us how the system relaxes from one state to another, so it's called relaxation operator as well. And gamma alpha gives us the various decay or transition rate. Gamma alpha gives us the decay or transition rate. Okay. To understand it, let us consider the case of a two-level system which relaxes via spontaneous emission. We have this two-level system. The excited state is represented by this state K1 and the ground state is represented by K0, and the system go from the excited state K1 to the ground state K0 by emitting some, say, photon, and this rate of transition is gamma. So as you can see in this example, we have only one decay process is there, and the system goes from K1 to K0. Therefore, the system relaxation operator, we can write it as it go from K1 to K0. So this is the system relaxation operator, and the Hamiltonian of the system, and say the excited state has energy E1 and the ground state has energy E0, then the basis of K0 and K1, we know that we can write the Hamiltonian of the system as E1 K1 bra 1 plus E0 K0 bra 0. This is the system Hamiltonian, and the Lindblad super operator LS is now, this is S rho S dagger minus 1/2 S dagger S rho. So all these are operators, minus 1/2 rho S dagger S. Okay. Now because S is equal to K0 bra 1, therefore S dagger has to be K1 bra 0, and this will give us S dagger S would become K1 bra 0 K0 bra 1, because this is normalized, this is equal to 1, right? So therefore we'll have simply K1 bra 1. And because of this, the Lindblad master equation, now we can write it as del rho del t is equal to minus 1 I by h bar h rho plus gamma. Now let me write the form of the Lindblad here. That is your K0 bra 1 rho 1. I'm just putting this result because S dagger S is equal to K1 bra 1, right? So therefore you just have this I'm writing S is equal to K0 bra 1, then I have rho here, and then S dagger is K1 bra 0, okay, and then minus 1/2 S dagger S is K1 bra 1 rho, then minus 1/2 rho K1 bra 1. So this is my Lindblad master equation. So let me just denote it by the symbol, say this symbol, say sum, S say. Okay, we can now find the time rate of change of the excited state probability, because you know the probability for the excited state is going to be given by the density matrix element rho 1 1, and which is nothing but K1 bra 1 rho K1. So basically this is the expectation value of the density operator with respect to K1 excited state. So this gives me the probability of the excited state, and from here I can find out what is the probability rate of change of the excited state probability. That would be P1 dot, okay, that means this is nothing but time rate of change of probability for the excited state. That is going to be equal to 1 rho dot 1, and rho dot is we already have here, that is this, we have rho dot is equal to this. So let me put the whole Lindblad master equation there. So I have time rate of change of excited state probability is equal to K1, the first term in the Lindblad master equation is minus I by h bar h rho, and here I have K1, and then this next term is the transition rate is gamma. Okay, so this is my transition rate, spontaneous rate is gamma, or that is the dissipation coefficient, and I have 1, and this whole term 1. Okay, now it can be shown that this first term on the right hand side here is equal to 0, because this is due to the reason, maybe we'll do that explicitly in the problem solving session and you can actually work it out yourself. It's very trivial. Because H is diagonal, in K0 bra 1 basis, as this Hamiltonian represents the system Hamiltonian when it is not interacting with anything. Okay, this H represents the system Hamiltonian when it is isolated, and therefore it can be written in the diagonal form, and you can work it out and show that the first term is going to be equal to 0. Then we'll be left out only with this term on the right hand side of this equation. Now you can actually work it out very easily. Let me just show you that this capital sigma here, let me work it out, and that's very trivial to work out because we have this summation sign is k0 k1 rho 1 k0 minus 1 half k1 bra 1 rho minus 1 half rho k1 bra 1, and this whole thing is its scalar product with k1, and you can immediately see that because k1 and k0 are orthogonal to each other, so you will be left out with minus 1 half 1 rho 1, then minus 1 half 1 rho 1. Okay, that's what you will get, and this is nothing but p1, and this is also p1, so you will have minus p1. So this means thus we have p1 dot is equal to, from this expression we have evaluated this, so p1 dot is equal to minus gamma p1. So this is the rate of change of the excited state probability, and similarly you can find out the rate of change of ground state probability, that is going to be minus of p1 dot, and therefore it is plus gamma p1. What about the evolution of the coherences, that is the off-diagonal elements of the density matrices? So off-diagonal matrix elements, say rho, you have here 0 1 is the one of the off-diagonal element, that is your 0 rho 1. Now if we find out the time rate of change of this coherence term of diagonal elements, so again you just have to put the Lindblad-Master equation here in rho dot, and then if you work out this algebra, then you are going to get minus gamma by 2 0 rho 1, or I can write gamma by 2 rho 0 1. So this tells us how this off-diagonal elements in the density matrix changes with time, and you can similarly find out the other element rho 1 0. Time rate of change of rho 1 0 is also going to give you minus gamma by 2 rho 1 0. So what you see, that Lindblad-Master equation gives you the full information about the evolution of the all density matrix elements. Now here the notable thing is that the off-diagonal elements of the density matrix also decay when the system transit or relaxes from the excited state to the ground state because of spontaneous emission. This decay of the off-diagonal elements of the density matrix is referred to as the phenomena of decoherence, because you see the off-diagonal elements is basically represents the superposition between k0 and k1, and from here as you can see that the off-diagonal elements also decay, that means the superposition is also decaying at a rate here in this particular example that we are taking of the spontaneous emission, the decay rate is gamma by 2. Now let us consider the case of a harmonic oscillator which undergoes decay due to the interaction with the environment. That means the harmonic oscillator undergoes damping. So we are going to discuss the case of a damped harmonic oscillator. However, before we go further, let me remind you about the quantum mechanics of a harmonic oscillator. You know, typically in classical mechanics, A harmonic oscillator, the most usual example of a harmonic oscillator is the so-called mass springs system, where a mass m is attached to a spring of spring constant k, and the equation of motion in classical mechanics, the equation of motion for the harmonic oscillator is written in this form: m time derivative, double time derivative of x, mx double dot is equal to minus kx. K can also be written as minus m omega, k is equal to m omega square, and omega is the oscillation frequency of this harmonic oscillator. If we want to write down the harmonic oscillator Hamiltonian in classical mechanics, we write it as h is equal to p square. P is the momentum of this mass, p square by twice m plus half m omega square x square. So this is the classical Hamiltonian for the harmonic oscillator. And if we go over to the quantum regime, in quantum mechanics, we can again write down the Hamiltonian for the harmonic oscillator. However, here, because these are physically measurable quantity, h is now going to be represented by the operator h dash, s cap here, and similarly p is a physically observable quantity, that is the momentum. So we are going to put a hat here, p hat, and x is going to be replaced by x hat. It's an operator now, and therefore the Hamiltonian operator for the quantum harmonic oscillator is going to be p square by twice m plus half m omega square x square. So this is the harmonic oscillator Hamiltonian in the quantum regime. However, we can write it in a different form as well. If we express this position operator x, if we write it as x ZPF, which is basically ZPF means 0 point fluctuation, A plus A dagger. A and A dagger are the annihilation and creation operator respectively, and x ZPF is square root of h bar divided by twice m omega. I am here very quick because I know that all of you have studied harmonic oscillator in elementary quantum mechanics. And similarly, if we define this momentum operator in terms of this annihilation and creation operator by this I m omega x ZPF A dagger minus A, then the harmonic oscillator Hamiltonian can be written as h is equal to h cross omega, h bar omega, A dagger A plus half, which can also be written as h bar omega n cap plus half, where n is equal to A dagger A, and it is known as the n is known as the number operator. Okay, now the energy eigenvalues for this quantum harmonic oscillator, as you know, it is En is equal to h cross omega n plus half, where n can take value 0, 1, 2 and so on. N represents the number of quanta in the nth energy state. Also, you note that h, when the Hamiltonian operator operates on n cap, which is the number state or the so-called Fock state, it is called the number state. It is known as the number state, or it's also called the Fock state. This particular state simply represents that there are n number of quanta in the state, and En is the energy eigenvalue n. So this is the energy eigenvalue equation for the quantum harmonic oscillator. One of the most important characteristics of a harmonic oscillator is that its energy levels are equally spaced. That means the difference between the energy levels between adjacent energy levels are always equal. So this difference is given by h cross omega, and that is very easy to see from this equation. En is equal to h cross omega n plus half, right? And for example, for n is equal to 0, we have this energy would be h cross omega by 2,
and then for n is equal to 1 we are going to have 3 h cross omega by 2. So therefore, as you can see, the difference is h cross omega. Similarly, for the next one it would be 5 h cross omega by 2 and so on. So difference between two adjacent energy level is always equal to h cross omega. Now the annihilation and the creation operator satisfy some important relation, very useful relation. You may be aware of that when this annihilation operator operates on this number state, you are going to get root n minus 1. That means this annihilation operator is taking you from the state n to n minus 1, and if the creation operator operates on the number state, it takes you to n plus 1, and this is equal to root over n plus 1 and number state n plus 1. That means you are going from the state n to n plus 1, that is the upward transition, and in the case of annihilation operator, this is in the downward transition. Also note that when this annihilation operator operates on the ground state, that means n is equal to 0. That means there are 0 number of quanta in the ground state, no quanta in the ground state. This is going to give you 0 because the annihilation operator cannot take the ground state any further below, because ground state is the lowest energy state. So with these tools at our disposal, let us now consider the case of damped harmonic oscillator at 0 temperature. And now damped harmonic oscillator means that the state is transiting from a higher energy state to a lower energy state. So we have a situation like this. Now suppose you are going from the state n plus 1 to, in the case of the damped harmonic oscillator, at 0 temperature, you are going from n plus 1 to n, and again from n to n minus 1 and so on. Okay, you are going in the downward direction. So it is very easy to guess the system relaxation operator here. So as you can see, you are going from n plus 1 to n. So the system operator, you can guess that you are going from n plus 1 to n. And even better if you write it the system operator as relaxation operator as a, because it is the annihilation operator. You are going from upward state to the downward state, and this is happening at rate, you are going in the downward direction at rate say gamma. So this is happening at the rate gamma. So you have only one decay rate, that is gamma, and in that case the Lindblad master equation is going to be rho dot is equal to minus I by h cross h, this is the Hamiltonian of the harmonic oscillator, h rho, plus you have only one transition, that is gamma, and the Lindblad super operator is going to be a rho a dagger, right? You recall you have this kind of form, right? So already we have seen it, so let me not repeat again. And the other two terms are going to be 1/2 a dagger a rho minus 1/2 rho a dagger a. So this is the Lindblad master equation for this damped harmonic oscillator. Now let us see how the probability to find n number of quanta change. Now probability to have n number of quanta is going to be given by the expectation value of this density operator in the number state, and if we are interested in the time rate of change of this probability, so you just have to write it as n rho dot n. So therefore you just have to put the Lindblad master equation here. The first term is going to be n minus I by h bar, the commutation h rho n, and the other terms are, so the second term would be this gamma, and here you are going to have it as n, the term in the bracket would be a rho a dagger minus 1/2 a dagger a rho minus 1/2 rho a dagger a, n cap. Okay, so it can be actually shown that this particular term, the first term, is a coherent evolution term. This is going to be equal to 0, and it is very easy and straightforward to show, and maybe we'll do that in the problem solving session to show it, but it's you can also show it, because you know that h is equal to h cross omega a degar a plus half. You can just put that form and do the simple mathematics. You will be able to show it. And because of the fact that the first term go to 0, so you are going to have p n dot is going to be, if you do the explicit calculation, very straightforward calculation, if you apply the property of the annihilation and creation operator, you already seen these two relations here which I have written here. You just have to apply that, and if you apply that, you can work out the second term completely, and you are going to get this term. It will give you n plus 1 p n plus 1 minus n p n. Okay, here you have this p n plus 1 is the probability in the n plus 1th state, and that is nothing but the expectation value of the density operator taken with respect to n plus 1th state, and pn is the probability, which is nothing but the expectation value of the density operator in the nth state. Now this result can be used to find how the number of quanta changes with time due to interaction with the environment. The number of quanta is given by expectation value of the number operator, or a degar a, that is going to give you the average number of quanta, and this can also be written in terms of probability as npn, which you know from basic statistical mechanics or probability theory. This is what you can write. Now we are interested in knowing the time rate of change of this number of quanta, that means d of dt a degar a. This is equal to d of dt, let me write it in this way, npn, and this pn dot we have already worked out, so let me just put that result. Pn dot is this expression we have, so let us put that here, and that's going to give us n is going from say 0 to infinity. Let me take the decay rate outside, and here in the bracket I have pn dot is going to be equal to n plus 1 pn plus 1 minus npn. Let me open up the terms. Then I have gamma n is equal to 0 to infinity. First term is n into n plus 1 pn plus 1. The second term is summation is going from n is equal to 0 to infinity n square pn. Now this particular term, if you look at carefully, this I can rewrite in this way also, because sum is going from n is equal to 0 to infinity. If this first n, if I replace it by n minus 1, the second one n plus 1 I am going to replace it by n, and pn plus 1 would be simply pn, and that going to make my calculation quite easy, and this I can easily work out. And if you see, if I open it up, then I am going to get minus gamma sum over n npn, and npn, this sum is nothing but the expectation value of a degar a, as we have already written here. You see, this is what we have written. So you basically get this rate equation d of dt a degar a. Now you can immediately write the solution of this equation. A degar a at time t is going to be equal to e to the power minus gamma t a degar a at time t is equal to 0. So this shows that the number of quanta decays exponentially with time, and the rate of decay is gamma.
With these two examples, I hope you got some idea about how to use the Lindblad master equation. In the problem solving session number 5, we are going to do some more examples. Now let me briefly discuss about the so-called Wigner distribution function or Wigner density, which is often used to represent a quantum state. Here again you will see the role of the so-called density operator.
Wigner density or Wigner distribution function W of xp is a great tool to compare quantum and classical mechanics. In the case of classical harmonic oscillator, we have already seen that the classical harmonic oscillator Hamiltonian H is equal to p square by 2m plus half m omega square x square. Now here x and p are the position and momentum variable and they are at equal footing, and the dynamics of the harmonic oscillator can be described in phase space. Most of you are aware of that in phase space the dynamics of a harmonic oscillator is represented by such kind of a plot where in the y-axis we have say p by m omega, and in the horizontal axis we have x, and the phase space plot for a harmonic oscillator for a given energy say E, where energy is E for this particular harmonic oscillator, then the phase space plot of the harmonic oscillator would be represented by an ellipse. Now the question is, can we extend this idea of phase space to quantum mechanics? It appears a no at first sight, because due to the uncertainty principle we cannot measure x and p at the same time. Still, it is possible to construct a probability distribution function wxp which should behave like a classical probability distribution function at high temperature. It may give us an idea about the classical quantum transition. Now let us say we are given the wave function psi of x in the position space and we want to know the probability in the momentum space. For momentum wave function is psi tilde p, and we know that this can be obtained by taking the Fourier transformation of psi of x from elementary quantum mechanics. Once again, you know that psi tilde and psi of x, psi tilde of p and psi of x is related by this Fourier transformation. We have this dx e to the power minus I by h cross h bar px, okay, and here we have this factor square root of 2 pi h bar, and in that case the momentum probability density is going to be psi tilde p of mod square, and which is psi tilde p into complex conjugate of psi tilde p and psi tilde p, product of these two, and this I can write as integration. There are 2 square root of 2 pi by h bar would be there, so we'll have 2 pi h bar, and we are going to have a double integration. So let me write it as like this: dx1 dx2 e to the power I by h bar p x2 minus x1, and I have psi of x1 psi star of x2. I hope you are getting it. It's very easy to see that we are obtaining the momentum probability distribution function density, probability density as this, and if you have followed this expression for psi tilde p, this Fourier transform pair, then you can immediately figure out that psi tilde p mod square is going to be given by this expression. Okay, now let us make a change of variables like this. Say let me take x1 is equal to x plus y by 2 and x2 is equal to x minus y by 2. That means now I want to go from the variable x1 x2 to the variable x and y, and while doing that, first let me check the Jacobian of transformation. So we are having x1 x2 and it is related to x and y by this transformation equation. So you have 1 half 1 minus half. Okay, and here this is the Jacobian. Now if you look at the determinant of this Jacobian, j of xy, this is going to give you minus 1 half minus 1 half. So magnitude is going to be equal to simply 1. So that means the area under the integral is fixed, is preserved. So integration dx1 dx2 is equal to integration dx dy. It's double integration, but we are now writing simply one integration. That implies that we are dealing with double integration. So therefore psi tilde p mod square is equal to integration dx dy divided by 2 pi h bar e to the power minus I by h bar py, and here you are having psi x plus y by 2 psi star x minus y by 2. Suppose we are allowed to take y is equal to 0. Let's say we are allowed to take y is equal to 0, then you will see that in that case I can write psi tilde of p square mod square would be equal to dx into psi star divided by, in fact you are going to have something like this, psi star of x psi of x, and this is nothing but the probability density in x in position, and therefore this is probability density multiplied by dx. So this gives us a clue that I can now define a function wxp is equal to dy divided by 2 pi h bar, then I have e to the power minus I by h bar py psi of x plus y by 2 psi star of x minus y by 2. If I define this function, then I can write psi tilde of p mod square is equal to integration dx wxp. So here this wxp acts like a probability distribution function, and this is known as the Wigner distribution function. Wigner distribution function. Okay, so as you can see, using this Wigner distribution function, if I just take an integration of the Wigner distribution function with respect to x, then I get the probability distribution function for the momentum. And similarly, you can show that you are going to get psi of x, the probability distribution function in position, you are going to get it by just taking the integration of this Wigner distribution function with respect to the momentum. This is going to give you the position probability density. Okay, let me go further. Because of the fact that generally you see these wave functions are not in pure state, they are in mixed state, so therefore I have to take the ensemble average. So therefore I can now write in general that w of xp is going to be, I can now write it like dy 2 pi h bar e to the power minus I by h bar py, and I have to take the ensemble average psi of x plus y by 2 psi star of x minus y by 2. Okay, now note that this density operator is k psi bra psi. In the position representation, I can write it as x dash, I can express it as say x psi here and psi x dash. Okay, so therefore this is nothing but the wave function in the position representation psi of x, and this is the complex conjugate of this position state. Okay, so therefore using this, what I can do, I can write this expression in the following form. I can now write w of xp is equal to integration dy divided by 2 pi h bar e to the power minus I by h bar py, and let me write it as rho of x plus y by 2 x minus y by 2, where rho is now the density operator, our usual density operator in the position representation. Okay, let me once again ask this question: what about the position probability density? As I said, it should be obtained by taking an integral of the Wigner distribution function with respect to momentum. Let me check it and let me see whether I get actually this mod psi of x square or not. So let us check that, and to do that let me go ahead like this. So I have here integration dp w of xp is from there I have that integration dy divided by 2 pi h bar. Okay, this is what I am once again writing: e to the power minus I by h bar py, and we have rho x plus y by 2 and x minus y by 2. This is what I have, and I can now write it as dy divided by 2 pi h bar, and this one, this integration dp e to the power minus I by h bar py is actually it is nothing but, in fact, 1 by 2 pi. This thing is equal to delta of y by h bar. This is, this is the Dirac delta function. So therefore this particular part I can now, using this, in fact, okay, let me write it like this. So I will have dp e to the power minus I by h bar py is equal to 2 pi delta y by h bar. So utilizing this result here, I have 2 pi delta of y by h bar. Okay, and then I am having rho of x plus y by 2 x minus y by 2. So this is my integration. So let me write it once again here. I have dp of wxp is equal to, I am getting it now as dy divided by 2 pi h bar 2 pi delta y by h bar rho x plus y by 2 x minus y by 2, and this I can further write using the property of this delta function. I know that delta y by h bar is equal to h bar delta y. So using this, users can look at into any mathematical physics book or engineering mathematics book. You will get this relation. In fact, delta of say ax is equal to 1 by a delta of x, right? This is a well-known result. So utilizing this result, I have dy delta y, okay, rho of x plus y by 2 x minus y by 2, and this is going to give me, simply applying the property of the Dirac delta function, I have here rho x x, and that is nothing but psi mod psi of x square. So you see, we have now shown you that just by taking the integral over the momentum on this Wigner distribution function, you are going to find the probability density in the position probability density. Now it is straightforward to show that this Wigner density function, if you take the full integration over the both position and momentum variable, that is going to give you 1, and that means that the Wigner distribution function or the Wigner density is normalized. We can plot the Wigner density distribution function for various quantum states. For example, the Wigner distribution function or the Wigner density of the ground state of a harmonic oscillator, quantum harmonic oscillator, can be plotted, and the plot is going to be of this type. Here you see it's just like a plot in the phase space. Now for the ground state wave function for the quantum harmonic oscillator, the contour lines are simply circles. We can actually go on plotting many quantum states for various systems, but generally these are a bit complicated and mostly computer programs are used to do that.
Let me stop here for today. The next lecture will be a problem solving session. I hope that many concepts will be more clearer to you after we solve some problems in the next lecture. So see you in the next lecture. Thank you so much.